Yes, good afternoon to all the students. Let us have a look at the syllabus first today. So we have got the first unit where the first unit we are having the introduction of the power BJT. We have taken SCR, power MOSFET, power IGBT. Today, if possible, we'll take the power diodes and then power BJT. But examination point of view, the SCR, and throughout the syllabus, we are supposed to use the circuits of the SCR. Right. Next, we have taken the commutation process and all those things. This is the theory, thyristor rating and production is the theoretical one. We'll see later on. Now, if you see the second unit, AC to DC phase control converters. So we control the speed of the motor, we control the output power of the motor by changing the firing angle, phase angle or delay angle. So it is called the phase controlled rectifiers. So principle of single phase fully controlled converter with R, RL and Rle load. Next, what type of converters we are having? Single phase off control. So we discuss all these things with respect to the yes, please log in with your name. One student has came with certain ID, okay, which cannot be accepted. Ask that student to come with her name or roll number. Okay, then we can admit easily to the class. So one link means we cannot admit. Right. Our student name is what? One student has just logged in with the ID. Let us go to the topic of today's class. Yes, today's class we completely discuss the derivative part, and next class we concentrate on the problems on fully controlled converters. So first, let us see what we have studied. Rectifiers. So first we are having resistor load, RL load and Rle load. So if you see the fully controlled rectifier, so why this transformer is used? What is the name of this transformer? It is not step down and step down operation performed by this transformer. It is called isolation transformer with the ratio 1:1. This transformer connects or disconnects the circuit. So directly AC voltage can be applied to the power SCRs, but here in order to provide the isolation, if required, this transformer is used as the isolation transformer to connect and disconnect the circuit. Okay, the ratio is 1:1. So we already taken the working principle of this circuit, but I want to show you the graph practically. So this is the input AC signal, we already know. So what is the output waveform for resistor load? First, let us check for the resistor load. So for resistor load, if you see the output voltage, the SCRs are turned, yeah, yes.
Number hello. What company the number 8.
Yes, Monica, please mute yourself. The SCRs during positive off cycle, when they are triggered or fired at firing angle alpha, you can see the output voltage. Then the SCRs T1 and T2 are on, the output voltage follows the input voltage, but SCRs are turned on at alpha. So output voltage we are having, let us check the explanation. So right, so during positive off cycle T1 and T2 are on, and this is the output voltage. Let us have the yes. Now let us concentrate on the current waveform. Examination also we must draw the input voltage, output voltage and output current. So if you see what will be the theory explanation. So we already discussed how the current flows, which SCRs are on. But these points right now what I am mentioning is what you are supposed to highlight in the examination. Case 1. Okay, everyone remember this one. Case 1 at omega t is equal to alpha. You can see the V0. Okay, at omega t is equal to alpha, firing pulses are given to SCRs T1 and T2. Okay, firing pulses are given to SCR T1 and T2. Now at omega t is equal to alpha, SCRs T1 and T2 are on. When SCRs are on, they transfer the input energy to output. Current flows through the SCR and the load. So current waveform also follows the voltage waveform, output voltage waveform. Now what's happening at omega t is equal to pi? Anyone? At omega t is equal to pi, if you see the input signal, the value is 0. Since the input voltage is 0, output voltage is also 0 and output current is also 0. So we say for resistor load, output current, output voltage follows the input, and from omega t is equal to pi plus alpha, all the SCRs are turned off, no current flows through the load. You can see here for the resistor load. So we cannot turn on T3 and T4 at omega t is equal to pi because input supply itself is 0. So all the next SCRs T3 and T4 are turned on at omega t is equal to pi plus alpha. So when omega t is equal to pi plus alpha, when SCRs T3 and T4 are on, current flows through the load from pi plus alpha to next 2 pi. So 3 cases we have to write. What happens at case 1? At omega t is equal to alpha, omega t is equal to pi, and omega t is equal to pi plus alpha. Same thing repeats here. So you already done with the waveforms. The theory explanation, once again I am repeating. At omega t is equal to alpha, SCRs T1 and T2 are on, current flows through the load. At omega t is equal to pi, input voltage value is 0, therefore current cannot flow through the load at this condition for resistor load. Once again, at omega t is equal to pi plus alpha, both the SCRs T3 and T4 are turned on. So what will happen at omega t is equal to 2 pi? At 2 pi, input voltage is 0. T3 and T4 SCRs will turn off naturally, and current flowing through the load is also 0. So once again, at omega t is equal to 2 pi plus alpha, we apply firing pulses to the SCRs T1 and T2, sorry. Therefore, T1 and T2 are off. This is a cyclic process. So now let us move to the derivative part. First, this during negative off cycle. Okay, what we have discussed. The theory, what we have discussed, the theory you can mention in the examination too. So now let us concentrate on this particular output expression. Okay, equation is visible clearly. Anyone confirm? Rle Load, average output voltage. Equation is visible to you, all the students. Expression not visible or visible? Anyone in chat box or else visible? Okay, right.
Yes, sir.
Okay, right, good. Average output voltage. So what is this word called average? So when we convert AC to DC, we are not going to obtain pure DC. Certain amount of AC components are also present, which are called the ripples, unwanted AC signals. So the output voltage signal, what we are getting, it is a combination of AC and DC components in this signal are called the average, which is approximately equal to DC. So what is the formula for average voltage? How to calculate the average voltage of this signal? So output voltage or average voltage. In order to calculate, in order to use this equation, we must study one basic. Let us go back to this particular slide. So we got pure AC supply. What is the average value of pure AC supply? Anyone? Average value means here positive off cycle, negative off cycle. So positive plus negative divided by 2 cycles, divided by 2. So it is 0. Average value of a pure sine wave is always equal to 0. Therefore, average value is defined only for what cycle? Off cycle only. If you see this graph, okay, in order to explain the average value, we must take only the off cycle only. I am just concentrating from 0 to pi. So what is the formula for average current or average value? The formula is area of the curve. This is the curve here. Okay, so area of the curve by length of the curve. So what is the length of this simple off cycle? It is from 0 to pi. What is the maximum value? 0 to pi for this off cycle. So area of the curve by length of the curve. So what is the name of this signal? Voltage. Voltage formula V is equal to Vm sin omega t. So denominator length of the curve is from 0 to pi, means pi minus 0. Higher value minus lower value. So denominator becomes pi. And what is the area? How to calculate the area? Integration. Total area we require. So integration of V of t dt. So what is the formula of V? Vm sin omega t d omega t. So that equation we keep here. So if you see this animation, the slides, in what way we can explain this derivative part of this particular topic, right? Average output voltage. So why we are getting this particular expression? You see the denominator is pi, that is the signal. You can check the signal. Output voltage is starting from alpha. Okay, for one positive cycle, it is reaching the pi. So what is the length of this curve here? It is from alpha to pi. So higher value minus lower value. So pi minus alpha we can take. But here, what is the length? It is, if you see the output voltage, it is reaching the maximum value pi. So denominator length of the curve is nothing but the, here it is nothing but the pi. So if you take the length from the 0, the denominator you are going to get the pi. Area of the curve, numerator. So for area we have to take the integration. Integration from where to where? The output voltage is starting from alpha and alpha to pi. Yes, any question? Some Chandrakala has raised the hand. Raising the hand in Zoom means any question you are having, you can ask, you can unmute. Question unte adagandi orena. Any doubt, any question? Or in chat box you can put the question. Okay, right, we'll see at the end of the class, right? So average voltage V0 is equal to this particular expression. Now we got area of the curve by length of the curve. So length is from 0 to pi. If you see the input voltage, higher value minus lower value, pi minus 0. So here it comes the pi. So numerator area, how to calculate the area? You must take the integration of this particular graph. So area says that integral from minimum value to maximum value. What is the minimum value here? Output voltage. It is starting from the alpha. So alpha to maximum value is nothing but pi. At pi it is equal to 0. You can see the signal. So alpha to pi Vm. So voltage signal. So Vm sin omega t. We are differentiating with d omega t. So how to explain this one? First you bring this Vm outside. Vm by pi it will come. Integration of sign is what, anyone? Integration of sign is minus cos. So if you see minus cos, you are going to obtain integration of sign. Here the equation is direct, but very soon in the next slide also I'll show you. But let us see how we got this expression. So Vm you bring outside, integration of sign is minus cos of omega t d omega t under the limits alpha to pi. So cos 180 cos pi minus cos alpha you are going to obtain. So what is cos 180? Cos 180 is minus 1. So minus, if you take common, you are going to get this particular expression. Okay, you just put once again on the paper, but at the end we got the clear explanation of this one, how we are splitting. So just again I repeat, area of the curve by length of the curve, area formula is this one. Vm you bring it to outside, integration of sign is minus cos, and minus again you can keep outside the bracket, cos omega t under the limits alpha to pi. So cos 180 minus cos alpha, minus if you are taking common, cos 180 is how much? Minus 1. So we are going to get the Vm by pi 1 plus cos alpha. So if I am using fully controlled converter for resistive load, what is output voltage we have to remember? Vm by pi into 1 plus cos alpha. So all the students, in order to do the problems, this is the formula we have to remember. So what is the current flowing through the load? Okay, current equal to V by R. So you can see current I0 equal to V0 by R. So if a power electron fully controlled converter is used to control the brightness of the bulb, how you are going to control? So we are going to control with the voltage, output voltage Vm by pi into 1 plus cos alpha. So after the theory, this is the derivation. Now we go for the Rle load. The derivations are not required. So let us check for the Rle load. Yes. Everybody know the circuit fully controlled converter 4 SCRs we have taken. Already I mentioned the best way to represent is inductor followed by the resistor. Okay, with respect to textbook. Now, so what are the graphs we are supposed to concentrate here for the fully controlled rectifier with the inductor load? We are having the AC supply input. Let us check the output voltage. Now, here you see all the students concentrate at this graph. So input signal is this one. Output voltage also follows the input voltage for inductor load. But what will happen to the current? The current flowing through the inductor, since it is an inductor load, current flowing through the inductor will not increase suddenly. Now you please concentrate on the current waveform. Current waveform has started at 0? No, it has started at alpha. Omega t is equal to alpha, and current is increasing in a sine wave? No, current is increasing in exponential manner or gradual manner. You can see the animation here. And at omega t is equal to alpha, the current flowing through the inductor has started. Inductor starts to energize, and now it reaches, you can see this one. So once again, I just for Rle load, you observe the input signal. Next we got the output voltage. Now current waveform, you can see what is the explanation. So current waveform starts at omega t is equal to alpha. It will not increase proportional to the input voltage. It increases exponentially. It reaches the maximum value. Current flowing through the inductor will become maximum at omega t is equal to 180 degrees. So here you can see input voltage is 0 at omega t is equal to 180. Output voltage is also 0, but current is maximum because we are using large value of inductor. Current value is maximum here. So, and next, in the current flowing through the inductor will never be equal to 0 at omega t is equal to 180. This is the most important objective type question. For inductive load at omega t is equal to 180, what's going to happen? At omega t is equal to 180, input voltage is 0, output voltage is 0, but the current flowing through the inductor is not 0, but the current flowing through the inductor is maximum. So when the inductor will release the energy completely. So after omega t is equal to pi, that after omega t is equal to pi, we are saying it as omega t is equal to pi plus alpha. You can see now the inductor has de-energized at this point. So in what way we have to give the explanation for the inductive load? After explaining the currents T1, T2 are turned on, case 1. Okay. So any student, I can ask the question. Remember this one. Case 1, what we have to write? Case 1 at omega t is equal to alpha. You can see we are assuming at 30 degrees at omega t is equal to alpha. SCRs T1 and T2 are turned on, and current SCRs T1 and T2 are turned on. Current flows through the SCR. Since we are having the inductor, current flowing through the inductor will not increase or decrease suddenly. It will increase in an exponential manner. So whenever current flows through the inductor stores energy and magnetic field is created. So at omega t is equal to alpha, current starts to flow through the inductor. Magnetic energy is developed across the inductor. At omega t is equal to pi, what's going to happen? Anyone student? At omega t is equal to pi, what's going to happen? At omega t is equal to pi, inductor current will become maximum with input voltage 0 and output voltage 0. That means since the current is flowing through the load, SCRs T1 and T2 are not turned off at omega t is equal to pi. They are turned off at omega t is equal to pi plus alpha, which is called the beta. So there are three cases. Case 1, omega t is equal to alpha, omega t equal to pi, and omega t is equal to pi plus alpha, which is equal to, we are saying beta. Beta is equal to pi plus alpha, that value. At omega t is equal to pi plus alpha, what's going to happen? All the at omega t is equal to pi plus alpha, the energy released by the inductor is completely energy released by the inductor is 0. Inductor releases the complete stored energy, and now the SCRs T3 and T4 are turned on. Once again, current flows through the inductor. You can see the second way. You can see here at omega t is equal to pi plus alpha. Once again, SCRs T3 and T4 are on, and now the current flows through the inductor. Once again, inductor starts to energize. You can ask, sir, what is actually this inductive load? Yesterday I mentioned it is representing the inductive load, means the motor, DC motor. So when inductor energizes, you can see the energizing here. When inductor energizes, motor accelerates, motor increases its kinetic energy and rotates in forward direction. Okay. So when inductor de-energizes, energy is released by the inductor, motor starts to de-accelerate. So these are the graphs which we have taken for the inductive load. Okay. You can see the notations here. Pi plus beta is nothing but pi plus alpha. Okay. So during positive off cycle, during negative off cycle, what is going to happen? In a simple theory words we can explain, but these three graphs are important, what we have taken. If any student is having the doubt, I'll repeat once again. Only three conditions: at omega t is equal to alpha, at omega t equal to pi, and at omega t is equal to pi plus alpha. What's going to happen? We have to discuss. So if there are any doubts are there, you please just I'll check in the chat box. Anyone student, any doubt? Chat box is filled with the attendance. Okay, any doubt is there, you can ask the question, unmute. Okay, any explanation also here? Of course, I'll provide the material, but in shortcut, you have to remember this one. What happens at these three stages? Right, during the interval, here in the theory, as we have mentioned at omega t is equal to, you can see first statement, omega t is equal to alpha, omega t is equal to pi plus alpha. So we have even introduced the omega t is equal to pi. Right. So now let us check the derivation. So those who are having the doubt how to derive this expression, so this part I will communicate here. Okay, so if it is clear, in order to explain this graph, let us complete this one. Fully controlled converter with alpha less than 90 degrees. In order to send maximum output voltage, we should have the minimum firing angle. So this is the graph. I'll explain this graph now. Even this one. So for your understanding, I just draw it. Okay, now the slide is visible, all of you. Anyone student confirm, please?
Visible, sir.
Visible, right? So these graphs I will try to explain. So what exactly is this fully controlled converter circuit can be used as rectifier and inverter. So I'll explain this particular slide also, but let us go with this one. So fully controlled converter with inductive load as well as Rle load can be operated as rectifier and can be operated as inverter. So what is this inverter? We'll see here. So if I'm giving the firing pulse at alpha equal to 30 degrees, let us say less than 90, maximum output to maximum energy is transferred from input to output. So here in this graph, they have shown one horizontal line. So this is the continuous current, what they are mentioning, but we have to show the energizing and de-energizing condition. So I'll explain this one clearly right now. Let us have the practical view. Right. So now what we have to give the explanation, let us draw this one. So we got the input is positive off cycle and negative off cycle, which is entirely the continuous process. Okay. So now I want to control the maximum speed. I want to achieve the maximum speed of the motor. In order to obtain maximum speed, what we have to do, we have to send maximum energy to the output. So what should be the firing angle? I should select the firing angle very much minimum. That means I am selecting alpha equal to 30 degrees here. So when you are using the firing angle as minimum, maximum energy of input is transferred to output. So what is the output waveform now? The output waveform will be starting from this particular point and it will follow the input waveform. So what happens to the current? How to draw the current waveform here? So current waveform will energize from exponentially, it becomes maximum at this point and again starts to decrease, which we have seen yesterday. So let us say I want to now I want to run the motor at minimum speed. So what should be the firing angle? Firing angle should be greater than 90. If firing angle is less than 90, motor rotates at maximum speed. If firing angle is maintained at 90 degrees, then motor rotates at medium speed. And in order to have the minimum speed of the motor, firing angle should be at maximum value. So now let us draw once again this particular graph. So now I am changing the firing angle in order to explain. So when this rectifier, so fully controlled converter with inductive load can be used as rectifier and inverter. So when to use the rectifier? When alpha is less than 90. So one second, let us check this. So now, in order to have the minimum speed, firing angle I am selecting greater than 90. Firing angle, let us say I am selecting as 120. Okay, here it is started. So when firing angle is maximum, what will happen? Minimum energy is selected and minimum energy is transferred from input to output. So this is the minimum energy transfer. So what will happen to the current? Current will energize here and current starts to de-energize. So what's going to happen? We can achieve the minimum speed. So when minimum energy is transferred from input to output, output voltage will be greater than the input voltage. So at this condition, the fully controlled converter is used as the inverter. So once again, we'll go back to this slide. Okay, so here they are explaining only one point. If alpha is greater than 90, what will happen? Minimum energy is transferred to the load. So no need to draw this particular graph, only this point you mentioned, because in Rle load we'll discuss later on. This particular graph is explaining it operates as a rectifier, converting AC to DC, and even it can operate as inverter, converting DC to AC, because output current is DC. If the firing angle is greater than 90, energy is transferred from load to the source. This is what we have written. Single phase full converter, RL or Rle load, with firing angle less than 90 acts as rectifier, and with firing angle greater than 90 acts as inverter, where power is transferred from load to the source. So this is the explanation we require here for this one. So let us move to the Rle load. So yes, derivation we are taking. So Rle load derivation we start. Yes, get ready for this one, all the students. Yes, what is average formula? Average value equal to area of the curve by length of the curve. Length of the curve is 0 to pi. So pi minus 0 is nothing but pi. So what is the area now? For Rle load, if you see the graph, let us come back to this basic graph in order to, yes. For Rle load, if you see, it is from alpha to pi plus alpha, alpha to beta. Okay. So Rle load, current is starting from alpha, and current is exactly becomes zero. Current becomes zero exactly at beta. Beta is equal to pi plus alpha. It is not pi. So what are the limits? Are limits for inductive load? Alpha to pi plus alpha or alpha to beta. Beta is equal to pi plus alpha. So that's why in our equation, while solving the equation for the inductive load, so we'll see how we got this expression. So let us go back to the equation. So now you see, output voltage is nothing but area. Area means integration from where the signal has started, from alpha to pi plus alpha. For inductive load, current value is not 0 at pi. Current value becomes 0 at pi plus alpha. So alpha to pi plus alpha, voltage with respect to average voltage with respect to omega t. So denominator is pi. So area of the curve by length of the curve. So once again you can see. So we got Vm alpha to pi plus alpha under the limits. Next one, Vm you can bring it outside as I mentioned. Okay, Vm is constant, you can bring outside. Integration of sine is what? Minus cos omega t. Sin omega t integration is minus cos omega t under the limits. Alpha to pi plus alpha. So cos of pi plus alpha minus cos alpha. So we can reshuffle the expression. You can see here, we can reshuffle this particular expression. So what's going to happen if you are reshuffling? So negative sign gets eliminated. Here cos 180 plus alpha equal to minus cos alpha. So this particular right hand side. So here we say V average equal to Vm by pi into cos alpha plus cos alpha. So I repeat here once again. Integration Vm you can bring it outside. Sin is nothing but minus cos. So minus cos pi plus alpha minus cos alpha. So we are interchanging the terms. Minus gets eliminated. So cos alpha minus cos 180 plus alpha. Sorry, cos alpha plus cos 180 plus alpha. Cos 180 plus alpha is nothing but minus cos alpha. So minus minus common we can take. So overall we are going to get the 2 Vm by pi cos alpha, this expression. You can simply substitute the value. So what is the difference between the resistive load and the inductive load? If you see, fully controlled converter with inductive load, it provides less voltage. Initially, what is the output voltage? Anyone tell me? Vm by pi into 1 plus cos alpha. Fully controlled converter with resistive load, the output voltage is Vm by pi into 1 plus cos alpha, which is greater than 2 Vm by pi into cos alpha. So output voltage is decreased. Very first class I mentioned. Fully controlled converter with inductive load, the output voltage starts to decrease. We should improve that one. How to improve? We'll see. That is the next topic. So no need to study for the discontinuous current. As per the syllabus, we are having the expression for the only continuous current. So be perfect with this expression. And output voltage value for fully controlled converter with inductive load is V0 equal to 2 Vm by pi into cos alpha. This particular expression. Right. So last class we have seen what is discontinuous and continuous current. Now this notation is important here. As I mentioned, what is output voltage formula? 2 Vm by pi into cos alpha. So if you remember one point, always output voltage is inversely proportional to the firing angle. So what is this characteristics? When firing angle alpha is 0, we get maximum output voltage. When firing angle is 90, we get 0 voltage. And output voltage will be negative if firing angle is nothing but 180 degrees. That means negative means what here? I want to control the speed of the motor in backward direction. So what should be the firing angle? Firing angle should be greater than 90. If firing angle is greater than 90, we say the motor rotates in backward direction. If electric train is present, it moves in backward direction. So this is what the firing angle should be greater than 90. Okay, so this graph is explaining that when the firing angle is 0, you can see here, firing angle is 0. So here, yes, when firing angle is 0, x-axis you see, what is output voltage? 1, it is maximum. When firing angle is maximum, output voltage is nearly approaching the negative values here. So this particular graph is explaining that firing angle is inversely proportional to the output voltage. We cannot say directly inversely proportional at different stages. When firing angle is 0, we get maximum output voltage. So now we move on to the Rle load. The similar expression you can see Rle load. Yes, what is the basic difference between Rle load and Rle load? Rle load says that we are not taking into consideration the back EMF of the motor. If any motor contains the armature winding, field windings, and then the back EMF. So back EMF, if it is taken into consideration, what is the effect of the back EMF, then the type of load is called the Rle load. So what's going to happen in Rle load? So first stage, we say firing angle is less than 90. When firing angle is less than 90, the back EMF value is very much less. Okay, the back EMF value is less than the input voltage. Therefore, power transfer from input to the load. You can see here same explanation: T1, T2 on, and then T3 and T3 and T4 are on. So during case 1, when the firing angle is less than 90, energy is transferred from source to load. Back EMF effect is very much less. So you can see this particular graph. Now the converter is acting as the rectifier. When the firing angle is selected as greater than 90, input voltage will be less than the back EMF voltage. Therefore, energy is transferred from load to the source. The same graphs we are going to draw here. Okay. So direction of the current and the graphs will be same. So here this is what they are explaining. Controlled rectifier operation is from 0 less than alpha less than 90. So when alpha is less than 90, source voltage is greater than the back EMF. Therefore, energy travels from source to load. During this process, the thyristor says T1 and T2 are turned on. Okay. Now, when the firing angle is greater than 90, now this is the second operation. If the firing angle is greater than 90, input voltage is less when compared with the back EMF. Therefore, energy travels from load to the source. Now, the fully controlled converter, it is called as the inverter, commutated inverter. So remember, fully controlled converter can be used as the inverter also if the firing angle is greater than 90 degrees. The remaining theory is same as the inductive load of the current flows. So the E expressions are also same. The output voltage is 2 Vm by pi cos alpha. The same expression you are going to get. Okay. So based on the syllabus, we are having the fully controlled converter with the resistor load and inductive load. Expressions we have taken just now. remember those expressions. But now I'm just giving one question. I am expecting the explanation from your side. So right, we are taking next type of full control converter, which is midpoint converter. Okay, so what is midpoint converter? We see the circuit. Midpoint converter, yes. Full control converters are of two types. One is bridge. Bridge uses 4 type of SCRs, and midpoint converter is 2 SCRs we are using. So nobody till now in the world has created the converter circuit which converts bidirectional to unidirectional current using 3 SCRs. Okay, you try with the any new circuit whether you are able to achieve the bidirectional current to unidirectional with 3 circuits or not. We will see. So what is this? How it is possible? What is the difference between midpoint and bridge? Output expressions are same, but constructionally, if you see the midpoint, this is called the tapping point. The point at which a load is connected to the circuit is called the tapping point. To this tapping point, we connect the load. Now the load is center tapped. We got the transformer, which is center tapped. The load is connected to the common point of the transformer. Okay. What will happen during positive off cycle? Remember only one simple point here. During positive off cycle, voltage at point A is greater than voltage at point B and N. N is the neutral point. Always its potential is less when compared with B and A. So during positive off cycle, voltage at point A is very much greater. Let me take the attendance screenshot first. Last 1 minute we are having. Okay, in the chat box also we'll take. Right, any questions? So here I will give you the hint. So during positive off cycle, voltage at point A is greater than voltage at point B and N. Therefore, direction of the current starts from the point A. You can see the current starts to flow from point A. You can see since the voltage at point N is very much low when compared with the B.